Hello, everyone. Let's have a look at this question on the normal distribution. It says the lifetime L hours of a battery has a normal distribution with a mean of 18 hours and a standard deviation of 4 hours. Alice's calculator requires 4 batteries and will stop working when any one of the batteries reaches the end of its lifetime. Find the probability that a randomly selected battery will last longer than 16 hours. So this is just the probability that any individual battery will last longer than 16 hours. So what we've got to work out here is the probability that L is greater than 16. Okay, so let's have a look at that and how, specifically, how I program it into my calculator. So let's have a look. I'm going to go across to distribution. And I'm going to select normal CD. And for my lower, I'm going to put 16. And then for my upper, I'm just going to put a really big value into my calculator. My standard deviation, I'm told, is 4. And my mean is 18. So I'll pop that in. And that gives me 0.69146. Okay, so that is part A done. 0.69146. Perfect, that's part A. Now, part B, let's have a look at that. It says, at the start of her exams, Alice puts 4 new batteries into her calculator. She has used her calculator for 16 hours, but still has another 4 hours of exams to sit. Find the probability that her calculator will not stop working for Alice's remaining exams, okay? Now, this is a conditional probability. So what we're finding here is the probability that the lifetime of a battery will last 20 hours, given that it has already lasted 16. Okay, so we want to know, because it's the Alice has got 4 hours left of her exams, we want to know what's the probability that the lifetime of a battery is going to be greater than 20 hours, given that it's already lasted 16 hours. Now, in this kind of conditional probability like this, when we have something given something, very often we can think about this as being a fraction where this is the denominator, because it's actually like a reduced sample space that we've got here. So another way to represent this is the probability of the lifetime of a battery being greater than 20, given that the lifetime is already greater than 16. Okay, so that is the probability that the battery lasts more than 20 hours, given that it's already lasted 16, is a fraction like that. Okay, now we worked out in part A the probability of the battery lasting more than 16 hours. So that was 0.69146. And now we just need to work out the probability that it's going to last greater than 20 hours. So let's return to our calculator and change the 16 to 20. So there we go. Pop that in, and I now find out that that is 0.3085. So I'm going to pop that down. That is 0.308537. Okay, like that. So we just work that out, and that turns out to be, when we pop that into the calculator, that gives us 0.44621. Okay, so whenever you see this, and you frequently do in these kind of normal distribution questions, the key is to think about that becomes the denominator. Okay, that's perfect. Now, what we found here is we found the probability of an individual battery lasting more than 20 hours, given that it has already lasted 16 hours. However, in Alice's calculator, there are 4 such batteries. Maybe Alice has got a calculator like this. So let's have a quick look. I'll just have a look in the back of the calculator. So here we are. So in the back of our calculator, you can see we've got 4 batteries there, okay? So we've got 4 batteries in the back of the calculator. And we've just found the probability that any one of them, okay, lasts longer than 20 hours, given that it's already lasted 16 hours. Now we need this one to last, and this one, and this one, and this one. And you may remember that in probability, whenever we hear that word and, we're going to multiply, okay? So what we need is this one, which is 0.44621, and this one, which is also 0.44621, and this one, which is 0.44621, and that final one, which is also 0.44621, okay? And they are all multiplied together because we need that one and that one and that one and that one, okay? Which we can think of is 0.44621 all to the power of 4. Okay, so when we calculate that, that turns out to be 0.03964. So we can see that Alice is playing a very high stakes game here. And in fact, the probability of her batteries lasting for all 4 of her batteries lasting to the end of her exams is about 3.9%, which is not very, very high. So in order to try and remedy this situation, what Alice does is she basically takes 2 batteries out of the back of her calculator and replaces them with 2 new batteries in the hope that this is going to improve the situation. So let's look at the next part of the question. Okay, so we've done part B there. So that's our answer for part B. Now, part C. It says Alice has 2 new batteries, only has 2 new batteries. So after the first 16 hours of her exams, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces these with 2 new batteries, okay? So she takes out 2 old ones, throws them in the bin, and basically gets 2 new batteries in there. Show that the probability that her calculator will not stop working for the remainder of her exams is 0.19923 significant figures, okay? Now let's think about the situation we've got now. So now we've got a new one, I'll put N for new, another new one, we've got 2 old ones, okay? So let's think about this, how this works. So we need this new one to last, okay? And remember, it's brand new. And remember that Alice has only got 4 hours left of her exams, okay? So we need the probability of a lifetime is greater than 4. In other words, that it will last more than 4 hours. And we need the other new battery, given that it's new, to last more than 4 hours. So that is life L greater than 4 and L greater than 4. And these 2 batteries, this is the same situation as what we had a moment ago, okay? So these probability of each one of these batteries, they're the same as they've already done 16, and we want to know, can they last 20 given that they've done 16? So for each of these 2 batteries, it's still the same probability we had before. So the 0.44621, the 0.44621, okay? Like that. This probability, again, we calculated, oh no, we haven't calculated that yet. Okay, so let's calculate that. Now, the probability that the lifetime of a battery is greater than 4 hours, when we put that into the calculator with the same conditions, is 0.99976. So a very, very high probability that the battery is not going to run out in the first 4 hours. So that's what we've got to work out in this case, when Alice has now swapped 2 of the batteries, 2 new and 2 old, okay? So we've got greater than 4, last 20 given that it's done 16, last 20 given that it's done 16. So we times all of those together, that one times that one times that one times that one, and lo and behold, that does in fact give us 0.19901. So it has improved the probability that, that Alice will get through the exam with her batteries to 20%. Okay, so which is actually 0.19923 significant figures. Okay, that's perfect. Right, we're getting there through this question now. Let's have a look at the final part. So it says, after her exams, Alice believed that the lifetime of her batteries was in fact more than 18 hours. She took a random sample of 20 of these batteries, and she found that their mean lifetime was in fact 19.2 hours. Stating your hypothesis clearly and using a 5% level of significance, test Alice's belief for 5 marks. So this question is really worth quite a good number of marks, worth a good 14 marks, as you can see here. So very, very well worth getting these marks. Okay, so first of all, we need to define our null and our alternative hypothesis. So H0, our null hypothesis, is that the mean is in fact 18 hours. So that's our null hypothesis. Now, our alternative hypothesis is that the mean is greater than 18 hours. That's what we're investigating, because that's what Alice believes. Now we've got a sample here from our normal distribution. And you might remember that when we have a sample from our normal distribution, we have mu, the mean, and we have the standard deviation over n. Okay, so that's the kind of form that it takes when we have a sample. So we've got L is going to, in this case, going to be normally distributed with a mean. We're going to have 18, and our standard deviation from earlier in the question was 4, and the sample size n is 20. Okay, there we go. So let's have a look at this now. We want to investigate the probability of this sample being greater than 19.2 hours. Okay, so let's work that out. Now, we have to be super careful about how we put this into the calculator. So we've got a normal CD, and my lower is 19.2. My upper, I'm just going to leave as some really big number. My standard deviation is 4, and my mean is 18. Okay. No, actually, my standard deviation is not 4. Now, this is where we've got to be super careful. Remember that this figure here is sigma squared. In other words, sigma squared is equal to 4 squared over 20. And when we put it into our calculator, we're putting sigma into our calculator. So we need the square root of 4 squared over 20. Okay. And that is actually the same as 4 over root 20. So when we have to be ever so careful about that, when we put that into our calculator, we need to put in 4 divided by root 20. Okay, I'm going to close that off there. So 4 divided by root 20. The mean is still the same. Okay, so I calculate that, and that gives me 0.0898. So let me write that down. So that is 0.0898. That's our probability. Okay, so now it's time for us to compare this with our significance level. We've got a one-tailed test, so we're comparing it with 5%. This is 8.98%. This is greater than 5%. Now, this is the bit where students very often get a little bit confused. But what this means is, as this figure is greater than 5%, it means that we are not in the critical region. Okay. And if we're not in the critical region, it means that we're going to keep HO. So if I write down, we're going to keep HO. Or we could say that there is insufficient evidence to reject HO. Okay, so we're going to keep HO, and that means that we could say that there is insufficient evidence. So insufficient evidence to support Alice's claim. Support Alice's claim. Okay, so we're going to keep HO, and there is in fact insufficient evidence to support Alice's claim. And that is our 5 marks. So I hope that you found that helpful with those 14 marks. I do enjoy that question. I think it's very interesting the way that Alice keeps on hanging on to these batteries, and then as soon as the exams are over, goes out and buys 20. I hope you enjoyed that, and I will see you in the next video.